A lot of acid-base chemistry involves the relationships between molecules that are conjugate to one another, that is to say, an acid and its conjugate base or a base and its conjugate acid. I want to look a little bit more deeply at that relationship in this video. So our learning goals are going to be about the relationship between conjugate acids and bases, and in particular I want to examine what their relative strengths are and what we can learn about that from these reactions. So first, let's review what a weak base equilibrium looks like. This is something we went over in an earlier video, and it basically involves a base reacting with water, which serves the purpose of an acid, to get a protonated base, which is the conjugate acid to the base, and hydroxide ion, which is the conjugate base to water. Now I've labeled all of these items here just so we can help keep them straight. I want to also point out that in this lesson I'm going to change my coloring scheme so that I'm always labeling the bases as blue, whether it's the base or the conjugate base, and I'm always going to label the acids as red, whether it's the acid or the conjugate acid. So before the colors matched conjugate pairs, now I'm going to focus more on their role as an acid or a base. Now the Kb for this reaction, we've seen before, is basically the product of the concentrations of the protonated base and the hydroxide ion divided by the concentration of the base, and usually less than 1. I want to compare this reaction and its equilibrium constant to the reverse of the weak acid dissociation equilibrium. So what I'm writing here is basically the reversed reaction for that. We have the conjugate base to the acid, which is A minus, reacting with hydronium ion to give the undissociated acid, which is now the conjugate acid to that base, and water, which is now the conjugate base to the hydronium ion acid. So if I write the equilibrium constant for this, since I've reversed the reaction for Ka, that equilibrium constant has to be equal to 1 over Ka. I hope you remember that relationship from earlier. Now since Ka is usually a number that's less than 1, if I divide by Ka, I'm going to get an equilibrium constant now that's much greater than 1. So in other words, for a weak acid and its conjugate base, this is a reaction we would expect to go very fully to the right-hand side. Now, what I'm really after is something a little different from this, and I want to point out the difference between these two reactions. In the weak base equilibrium, the acid is served by H2O, whereas in the second reaction, the acid is served by the hydronium ion. And what I'm really interested in learning something about is the relative strength of the base that is conjugate to the original weak acid. In other words, I want to know about the base strength of A minus. So let's see if we can get a handle on that by looking at some further reactions. What we're interested in is getting to know what the Kb is for this particular reaction. We want to know how strong a base, the conjugate base, is relative to water. That will give us a good comparison point. So for this reaction, we would have a Kb that would have this expression, the concentration of Ha times the concentration of hydroxide divided by the concentration of the conjugate base, A minus. So how can we get to this? What do we need to do? Well, one thing we can do, it may not be the first thing that occurs to you, but you could multiply this by the Ka of Ha. Now let's see what we get when we do that. So we have the Ka of Ha times the Kb of its conjugate base, A minus. So those two expressions would look something like that. So the Ka is coming from there, and the Kb is coming from there. And I hope you can see that we've faithfully reproduced the forms of those equilibrium constants. Now notice that they have several items in common. In fact, they both have Ha, the weak acid, and they both have the conjugate base to that weak acid, A minus, but they're switched in numerator and denominator. So in fact, they're all going to cancel each other out when we do this multiplication. What that results in is that the product of these two equilibrium constants is just going to be the hydronium ion times the hydroxide ion, and we know what that is. That's equal to Kw. So while this may not have been the first thing that occurred to you, by making this multiplication, we actually have an astounding and great relationship to utilize here that is always true in aqueous solution, that the Ka of a weak acid times the Kb of its conjugate base is always going to equal Kw, which in fact is a constant. So we have this wonderful reciprocal relationship between the Ka of a weak acid and the Kb of its conjugate base. And in fact, we can write that explicitly like this. So now, if I know the Ka of a weak acid, I can easily get, very automatically using this formula, the Kb for its conjugate base. And this relates to all conjugate pairs. So, I haven't specified anything about the weak acid or the weak base. We could also generate this for a base and its conjugate acid. As long as the two are conjugate pairs, they will have this relationship to one another. So let's see what this implies, though, about the relative strengths of these things. So they're inversely related. That's what this relationship means. So that means that if Ka is big, then Kb will be smaller. And if Ka is small, Kb will be larger. So that tells us that we have these complementary relationships, that if it's a stronger acid, its conjugate base will be comparatively weaker. If it's a weaker acid, then the conjugate base will be comparatively stronger. So this is a way that we can not only compare the strengths of weak acids with one another, but we can also compare the relative strengths of their conjugate bases with one another. So let's see what that looks like. If I look at, for example, formic acid and acetic acid, by looking at the Ka values, I see that formic acid has a Ka value that's about 10 times that of acetic acid. So it would be the stronger acid in general. What can I say about their conjugate bases, though? Since they have that relationship between their two acids, I can say that the conjugate bases for them, the conjugate base for the formic acid is formate ion. That's going to be a weaker base than the conjugate base for the acetic acid or the acetate ion. So this is a nice relationship that we can use, and when we learn more about pKa tables, we'll be able to put this to good use to learn something about the relative strengths of both acids and bases.